Good evening again. Welcome to the Honest Investigators Talk Shop show. And we're happy to welcome you here once again to our show where we're discussing the reciprocal system of physical theory, the RST, that is part of our effort to explore the physical universe using Dewey B. Larson's new system of physical theory that we call the Reciprocal System of Physical Theory. And so here's our new YouTube channel, and this is number 4 in our series, Scalar Mathematics for Scalar Motion and Scalar Motion for Scalar Physics, Part 4. So we welcome you here. My name is Doug Bundy. I'm president of the Larson Research Center, where we are unveiling the universe of motion. Today is Saturday, January 30th, 2016. In parts 1, 2, and 3 of this series, we presented a general overview of the work and purpose of the LRC and the major acronyms employed throughout these lectures. So please refer to the videos of those lectures for orientation type information. We would have to repeat a lot of it, so we don't want to do that and take up too much time each show. But they're available on our YouTube channel, as well as on our Google Plus page, and also our website, which are all entitled LRC Physics, excuse me. So you can go to lrcphysics.com and see all of our programs there. Okay, well, last week we introduced and began to discuss the new multidimensional scalar number system, which, as was pointed out then, a composite system with 3 basis units, the square roots of 1, of 2, and of 3. Well, this probably seems really bizarre to the uninitiated, but it stems from the recognition of the unity that exists between the binary expansion of the tectactris, the Greek tectactris, and the geometric equivalent of that expansion in 1, 2, and 3 dimensions of the 2 n-cube progression of numbers, the progression of what we now call Larson's cube, or the LC. And since the 2n-cube progression is a mathematical progression, perfectly expressible as a geometric expansion of points, lines, planes, and cubes, it would be perfectly suited for studying our 3-dimensional motion in discrete units with 2 reciprocal aspects, space and time, which we have assumed is the basis of all physical phenomena experienced in the universe. But alas, clearly it is not. And the reason for this, of course, is that the expanding universe expands in all directions defined by 3 dimensions, which is an infinite number of directions, not just the 2 directions or polarity, directions in quotes that we use, or polarity, plus and minus in 1 dimension, and so on. It's not just those numbers, but an infinite number of numbers, if you will, that can be defined in those 3 dimensions, and that are denoted by the 2-cube progression, 2n-cubed. The challenge of reconciling this difference between the mathematics of discrete numbers and the reality of continuous physical magnitudes has defied mankind's efforts since ancient days. Now, let me begin here by pulling up our and sharing our slide presentation, and you will see here then that we have I got ahead of myself here, but at any rate, what was I saying? Let me stop this for a minute. I was thinking I needed to have that pulled up, but Actually, that was premature. Hold on just a second. Okay. Well, and so what I was talking about is this failure between discrete numbers and continuous magnitudes. And we talked a little bit about that last week. But the most modern failure to accomplish this reconciliation between the two is prominently published by the community of legacy system theories is the incompatibility of its theory of the very small and its theory of the very large. That is the theory of quantum physics and the theory of general relativity. Both are needed to adequately explain nature for our modern theorists as observed, but they both can't be true because they're incompatible. One is discrete and the other is continuous, and what is needed by one is disastrous by the other, so they can't be reconciled. Now, our own approach to this differs completely since we are required to construct the entire universe of physical phenomena from nothing but discrete units of three-dimensional motion. Okay, now last week I was pull this up now. I was attempting to explain at least, the development of a new mathematics for this purpose that reveals that the 2n³ progression contains diameters, circles, and balls, as well as lines, squares, and cubes. We recognize the applicability of the Pythagorean theorem to the progression of this 2n³ progression, and that makes a big difference. This is done by expressing the n of the 2n³ progression as 3 different units, each derived from the hypotenuse of one of the 3 right triangles found in the progression. Now, you'll have to refer to previous lectures for the details, but please note the following caveat. Last week, as I was trying to explain this, I became confused towards the end of the last lecture and presented some misleading information on it, but I promised to correct it in today's lecture, and so this next slide shows the correct information. We've seen previously how the mathematics of combining these LCs, Larson's cubes, as the progression goes on, the 2n³ progression goes on, and how that combining those changes the n in the progression. So it's 2 to the 1 cube, 2 to the 2 cube, and so on, but that can be changed with these 3 numbers. Now, here's the rationale. It turns out that just like the stack of cubes, the 3 balls of the LC contain 3 sets of 1D, 2D, and 3D scalar components in each combo of units. So if we take a slice of the let's just start with the 2 by 2 by 2 cube, 2 by 2 by 2, that equals 8 cubes, and we slice it in the middle of it or collapse it down to 2 dimensions, we would see that we have 3 units that are defined in there. The normal one, which we'll describe as, or we'll define as the square root of 1, coming from the 3-dimensional Pythagorean theorem, where the square root of the sums of the 3 squares involved in the 3 dimensions become a unit. So when we're in 1 dimension, we see here that that's one of the 3 terms is populated. Then when we're in 2 dimensions, then we see 2 of those terms populated under the radical, and then in 3 dimensions, all 3, which that gives us then these 3 radiuses that are actually in the LC. If we take the radius of the ball that just fits inside the 2 by 2 by 2 stack of 8 unit cubes, we see that its radius is 1, or what we could call the square root of 1, because it's the same. And then, but if we draw a line from the very center of intersection of those cubes out to the top, in just going in 2 dimensions in the X and Y direction, then we see that that square root, or that result of the Pythagorean theorem is the square root of 2. And then as we do the same thing, and I can't show it very well here, but this is going out to the 8 corners, or one of the 8 corners of the stack of cubes. So it's going to be longer than the square root of 2. It actually turns out, by Pythagoras' theorem, the sum of 1 squared plus 1 squared plus 1 squared, which is the sum 3 squared, and or 3, and the square root then of 1 plus 1 plus 1 is square root of 3. So that's our third radius that's in there. And so we can depict it by taking this slice, because if we slice through it, and you can see the thing is here too, and this is where I got confused trying to explain last week, that each one of these, of course, has a 3D component. It has a diameter. Let's take the black one, for instance. It has a diameter, and it has also an area that with that radius equal to the square root of 1, and you can see it's like a quadrant here. If you could see that would be equivalent to the 4 squares. So we have listed over here the various components of each of these components that are in the stack, if you will. Of course, one of them is outside the stack, but that are defined by the stack. So if we take the inner volume, the black one here, the inner volume, its diameter is 2 times 1. You can see that very easily there, and which is 2 times the square root of 1. If we take the inner area, that would be 4 times the square root of 1, right? I mean, you got a quadrant here, and I don't show it very well here, but in the bottom, but you got another quadrant, and you got 3 quadrants. These are 3 slices of pi, and their radius then would be equal to the same, the radius of 1, but there are 4 directions, so there are 4 quadrants. And then, of course, if we take the cube of this ball, if we looked at it, we'd have to use the radius, and we'd have to cube it in the formula for volume, the constant times r cubed. So r cubed, though, is still the square, r is still the square root of 1, and so, but we have the 8 directions that we spoke about. So now in the inner ball, I hope that's not so confusing now. We've taken one ball at a time. The black ball has 3 colors, we'll say. The one-dimensional, have 2 directions, one this way and one that way. Then the 2-dimensional is in 4 directions. And then in the 3-dimensional case, it's 8 directions. And they all use the square root of 1. So that's why they're represented here in the 3 colors. And the same thing for the middle ball, the red ball. It has a diameter. It's not shown here, but you can see that its diameter, if you bring this down, is the square root of 2. And in opposite directions, the diameter then would be 2 times the square root of 2. So our one-dimensional component then for the middle ball is 2 times the square root of 2. You can see why it was so confusing, how I got this fouled up. I had made some typographical errors in the slides, and when I tried to fix them, I got really confused. But now for the 8 directions of the middle ball, and if you want to understand how each one of these has 14 directions, go back to our previous discussion. But for the cubic, or for the volume, or for the 3-dimensional case of the middle ball, the red ball here, we have 8 directions times its radius, which is the square root of 2. And then the same thing for the outer ball, the blue ball. It has a black, a red, and a blue set of geometric figures in it as well. So 1D, 2D, and 3D. So that shouldn't be too hard to understand. We've got in whatever slice of LC we take, we would be able to define these 3 balls, and each one of them would have these number of directions times its radius. And we've got three radiuses here. The one, radius of 1, the square root of 1, square root of 2, and the square root of 3. Okay, now, hi there, Roy. My brother's joining us here.
Hi, how you doing?
Glad you made it in. We just got started. You might want to just try to, it's going to be a little difficult to hang in here, but if you got some question, just feel like stopping me, and I'll go ahead and address it. But welcome to the show, and if you want to go ahead and mute your mic, we'll just continue with the presentation.
Okay.
All right. Great. So anyway, so here we are. We're talking about this slide here, and I'm trying to correct the mistake that I made last week in the progression. I think that's clear now. Well, we have in this 2n cubed progression, we have 3 continuous magnitudes that can be defined, as well as the lines, squares, and cubes that we're used to. And we've just discussed how they each have 3 dimensions as well, and how those dimensions would define magnitudes based on their own radius here. All right, so going on then, this then gives us 3 3D number lines. And so as we talked about the normal number line that we use, you can think of it in terms of the integers, where we have 1 over 1 as the identity element in the group. And then as we go to the left, we go what is normally considered negative numbers, but you see that's just the difference between the denominator and the numerator. If you take a numerator of 1 and subtract the denominator 2, you get a -1. If you take 1 and subtract 3, you get a -2, and so on. So this is the number we use in the fixed coordinate system, where we, at the origin of the coordinate system, we have the number 0. But in reality, especially in our system where we're using space over time or motion as our numbers, then when that motion is 1 unit of space for 1 unit of time, we're at the datum, what we would call the datum of that. And so going up, we would have 2 units of space for 1 unit of time, or actually this is the reciprocal of that. 2 units of 2 units of space increase for 1 unit of time, 3 units of space for 1 unit of time, and so on, which gives us the positive numbers if you take the difference between the numerator and the denominator of 1, 2, 3, and 4. So that's the number system that we're all familiar with, that we're taught when we're in school and so on. But now that we see that that comes out of this continuous system with the square root of 1, and that we have 2 others in that 2n cubed progression, then we can look and see that we can form another analogous number system, but quite different. Here, if we subtract the square root of 2 from the square root of 2, of course, the result is still 0. But in this case now, it's when we have 2 units of the square root of 2 over the square root of 2, then we get, and we take the difference, we get 1 times the square root of 2, 2 times the square root of 2, 3 times it, and 4 times it that way. And then the negative, because now we are, our unit is down here in the denominator, so now we get the negative numbers. But these numbers are quite different than those numbers. 1 times the square root of 2 is the square root of 2. 2 times the square root of 2 is the square root of 8. 3 times is the square root of 18, and 4 times the square root of 2 is square root of 32. Quite different from these numbers up here, and yet we see that they are part of our 2n cubed progression. And then, of course, we come down here where our unit now is a 3D unit, which is the square root of 3, and of course the same thing. And so we have these numbers. Now, this might seem bizarre, but it comes right out of the mathematics of the 2n cubed progression. So, but then the question is, which is the real ball? Which is the real 3D? If we want to use this 3D continuous magnitude, which one is it? Is it the black one that fits inside the stack, or is it the red one that fits around the 2 dimensions of the stack, or is it the blue one that the stack fits into? We know that the black one, of course, is much less than 2 to the third, and the blue one is much more because 2 to the third fits inside of it. So, and then we have the red. It's kind of like Goldilocks, right? the different sizes, but the red one is in between, and yet it's not the exact thing as well. So our question is, which one do we choose? Do we average them out or what? Well, the answer, I think, is here. We can see that for one-dimensional, we could use the V, this is volume, inner volume. So we could use the inner ball, that we call it, because it has exactly the same number in the one-dimensional case as the stack does. Then when we move to the two-dimensional case, that has exactly the same magnitude as the diagonal in the four square or 2 squared case. So 2 to the 1, we could use 1D. 2 to the 2, we can use this diagonal. And then when it's 2 to the third, we use the actual exact diagonal in the stack. Does that make sense? And so now what's really interesting about that is that that corresponds, and now that we have 3 numbers and 3 number systems that we can deal with, now we have something that's equivalent or at least analogous to our electric dimension, because the space-time dimensions for electrons is one-dimensional. And for the magnetic dimension, the Weber is used in the SI system, and that is the square. So we could use that for our magnetic calculations, the square of T over S, of energy over time over space, which is the dimensions of energy. And then this is wrong. This should say 3D. Oops. Sorry. Oh, wow, man, I'm all fouled up here. Okay, that is a mistake. I didn't catch that. That should say 3D is equal to T cubed over S cubed, which of course works out in the dimensions of mass. So you see, we have different units for whatever calculation we're making. For electrical calculations, we'd use the square root of 1. For magnetic calculations, however, we'd switch to the square root of 2. And for mass kinds of gravitational sorts of calculations, we would switch to the square root of 3. Now, I know that seems bizarre, but it's a new way of doing things. So here's a way of showing it in terms of the number system. Then the electrical magnitude or charge is one-dimensional, so we use the normal numbers that we have, and we know that that works out for us so far in our calculations of charge. It works perfectly for the proton, for the electron, for the neutron, and for the atom. It all works perfectly in here, but it doesn't work for this. And the proposal then is that when we go to calculate the dipole magnetic moment of the electron and the proton and so on, that we then would need to switch to this 2D unit, which is equal to the square root of 2, and use its number line. And then when we go to mass, which is magnitudes of matter aggregates, we would go to our 3-dimensional unit. So that's the proposal. I don't know exactly how it's going to work out, but that is where we would want to try to go. with our system. So then there's another aspect of this, the dimensional exponents versus the algebraic factor exponents. We have this wonderful equation that nobody's really been able to understand except in terms of what it gives us, that energy from Einstein, we get it, energy is equal to the mass m of matter aggregate times the speed of light squared. And of course, that's produced the atomic age. And so it's been revolutionary. But the thing is that if we take these dimensions, since energy is time over space, and we put that as equal to T as, we represent it as T over S. And so T over S cubed times S over T, which would be velocity squared, is what the equation tells us. But that could also be just factors in multiplication. If you multiply TS times TS times TS, which is TS to the third, and then divide it by TS times TS, which is TS to the squared, you're going to get TS. And so there's nothing really physical in that equation. So we could say, well, we know there's something physical because we got atomic bombs and so on. That kind of proved it. But as far as the mathematics is concerned, it doesn't tell us anything about what physically is actually happening. So the dimensions of energy, T over S, can be looked at as just the inverse dimensions of velocity, S over T. But what does that mean? It's only when S over T is equal to the speed of light, almost 300 million meters per second, does the energy calculation work. So what connection does light have with mass and so on? The equation doesn't tell us that. But if we look at the natural progression chart that we've used in a couple of these presentations, we can see that there is something very, very interesting here that goes right along with our number system. If we recall now, if time is progressing in the vertical axis here along this red line, and space is progressing along this blue line, and it's doing it we can consider it in units, then 1 unit of space would get, for 1 unit of time, would give us the square root of that. And so 1 squared plus 1 squared is 2 squared, and the square root of 2 squared is 2. So what we end up here is the progression that we can plot in terms of velocity. And that's part of our assumption that space is progressing in our natural system as time progresses. Now we can see this just as an aside. We know that time progresses. We measure it with a clock, but we didn't know that space was progressing as well until the modern age, when observations showed that every galaxy is moving out away from every other galaxy, and it's not like they're moving through space. Space itself is expanding, and so we represent that here in the horizontal axis, and we also then represent the expansion of time in the vertical axis. And what that gives us, with the right expansion, it gives us c, the speed of light, as a 1 over 1 unit of space for 1 unit of time. And so the result is a change in space and a change in time of 1 unit each gives us then this line, and that represents the speed of light, c. Now, when we take that and introduce those, and in order to understand all this, I can't repeat it each time again, so you have to go back to the previous lectures to understand that. But here we're saying, well, there could be the only change from unity. This is unity, 1 over 1 and 1 over 1 continue, 1 over 1, 2 over 2, 3 over 3, so on, which would be the speed of light. But if space oscillated, say in the expansion of 1 unit, it collapsed back to 0, and then in the next unit of time, expanded back to unit value, and then collapse and so on. So we have this 3D oscillation. Then that would change our 1/1 progression of space to 1/2, because we would be going back and forth over the same unit as far as space is concerned. And in one cycle, it would go down 1 and up 1, and then, but that would be 2 units of time. And vice versa for the other side, 2/1, because as time oscillated, and you can see this is represented here, this would be a 3-dimensional expansion contraction of time. I know that's bizarre for beginners, but that would produce this part of the equation. And as it went along, it'd be 2/1, 4/2, 6/3, and so on to 2n/n. So this is an important thing to understand, because excuse me, I just kind of lost my place here. But the intuition here that we have is that it goes right along with the number system. This is amazing. If we look at this physically and numerically, we're seeing the very same thing. So the viability of this approach now, it remains to be seen. We don't know for sure, but you can see what happens if we carry this out to understanding the number system. Just bear with me here for a moment. I lost what number slide we're on. Okay, we're on number 8 here. So they're not numbered here, and I forget where I'm at. Oh, darn it. This is crazy. Okay, now let me catch up here where I was. So my point is here that these numbers, these vibrations, cause this orthogonal change in the natural progression. So if we look now at what that means in terms of our number system, if we assume these continuous reversals in the quote direction of one of these two magnitudes, we see the exact analog to our number system emerging. Let's choose the 1D unit equal to the square root of 1, and as the unit of both space and time, so that the unit equation of the ST progression along that diagonal would be 1/1, and we'd say that would be equal to C. But now this one, see, in our regular math, what's 1/2? 1/2 would be 0.5 C, and this would be 2 C. So now I'm back to where I wanted to be. So we need to understand what is happening here with the correct algebra of these number lines. They depend upon two interpretations of numbers. We have this part of our number, the integer part, where 1/1 is equal to 1, but 1/2 is normally considered 1/2, or 0.5 C in this case, where we're considering 1/1 to be the speed of light, C, and then over here it's 2C. The speed of light twice, and that's just as a result of our natural progression. So if we then look in our number system, that where this the difference between the denominator and the numerator that we use in a fixed coordinate system, then 1 minus 1 is 0, and 1 minus 2 is -1, and 2 minus 1 is 1. So that gives us a totally different result. But what we have to do is understand that in this case here, the space progression is effectively eliminated by the space oscillation, and in the other case, the time progression is eliminated by the time oscillation. So we get these two results. But now, if we put these three together, like in this slide here, we can see that there's a whole different way of looking at the same thing, two different ways of looking at the same thing. If we multiply, or let's say in this case we're going to add, we add these numbers, 1 over 2. This is the number line. We just take the number line as far as we can. It's equal, not as far as we can, but as far as we need to in this example. And we see that we could add these three together, and what we get is a total of 4 units in the numerator and 4 units in the denominator. Well, if we add these two, we get -1 and a +0 and a +1. That's going to give us 0. So we get totally different results. And yet they're the same number system. See, so we need to understand that there's two interpretations that we need to recognize here. All right, so if we put these together, oh gosh, I forget to change the focus. If we look at the one interpretation, and we need both of them, but if we look at the one interpretation, the 1 over 2, and then the 1 over 1 would be here in the middle, and then 2 over 1 would be on that side, we could understand that there's a way of interpreting these that is quite different than we're used to. We can see that if we multiply them or add them, we can do both at the same time, both the numerators and the denominators. And if we do that, we kind of have to take them as a balance, as something that we can see in terms of a pan balance or a playground teeter-totter, if you will. There's only two conditions that a pan balance or the teeter-totter can find itself in. It's either going to be balanced or it's not balanced. And if it's balanced, the difference between the heights of the two pans or the opposite ends of the teeter-totter is 0. If it's not 0, then a greater magnitude exists on one side or the other, as we can see here. So in this case, it's balanced. We've got equal weights. But in this case, on the left, we've got the number 2, which if it were a weight would be heavier, and so it would unbalance in that direction when we only have 1 on this side. Of course, if we had 2 on this side, then we get the balance again. Or if we did 2 on this side and keep 1 on the other side, we get unbalanced, but in the opposite direction. So this is really something that we normally don't think of numbers, but since this is an analog of our number system, we could take these 3 points, if you will, the one on the left, one on the right, and the one in the middle, as numbers, and then add those. And that's what we do. We've explained that in our previous slides in our ST units, where we're combining units of space and units of time. But since they're on the either side of the unit speed, these units of motion then can unbalance the equation in one of these two directions. But now, not only that, but see, it depends on which side of the teeter-totter you're looking at it from. Because let's say you're looking at it from the red side. There's a red side and a blue side to the fulcrum here. And let's say from the red side, now on your left hand, you say, oh, wow, well, there's 2. It's unbalanced in this direction because there's 2 on the left and there's only 1 on the right. So that gives us that unbalance. But then if we go walking around to the other side of the same teeter-totter without changing anything, now the 1 is on our left-hand side and it's up in the air. And on our right-hand side, the 2 is heavier, and so it's on the bottom side. But if we're talking about speeds, which we are, and the balanced speed is the speed of light, so if we go 2 times the speed of light from over here, well, that's going to be allowed, right? But the same thing if we walk around to the other side is not allowed, because now it looks as if we would be, in this case, it would be allowed, because the 2 on our right-hand side is below the speed, the balance speed, which would be the horizontal line. And over here, it's also below that line. But this one would not be allowed. So if the balance were the other way around, we wouldn't allow it because it's over unity. We say that over the speed of c. We don't allow that. So if we change the balance here, then we would run into trouble with the legacy physics. All right, so it turns out that our reciprocal point of view of the natural progression is different depending on which point of view we take. We've got a space over time, or SOT sector, which is a view of our number line that we are familiar with, the 1 over 1, 1 over 2, the 2 over 1 on the right. So this way we're going positive, this way we're going negative. If we take the fixed coordinate system, this would be 0, this would be -1, this would be +2. But then when we go to the other view from the other side, where time over space, or the time TOS sector we call it, we get a view of the inverse number line. Now our negatives are, and see, we've written them like you would see them in the inverse. So 1 over 2, where we're getting smaller than 1 or lower than unit speed in the negative direction, is now going to our right, and increasing in the positive direction is now going to our left. So this is extremely important to understand, and is very straightforward. You could just see if you wrote this on one side of the glass, even like they do on the ships, right, in the aircraft carriers where they're tracking things. So if one guy standing on the side of that glass writes in crayon this number line, the guy on the other side of that glass would see it written like this. And it would be just depending on which side of the glass that you are, of which of these magnitudes you see. Now you might think that, well, that doesn't make any difference, but physically it does, because it turns out that we can then get 2 sectors out of our universe: the material sector and the cosmic sector. And in the material sector, vector motion is in space, but in the cosmic sector, vector motion is in time. In the material sector, we write velocity as space over time. But in the cosmic sector, we write velocity as if it's viewed from our material sector as T over S, and we call that energy. But if we look at our energy, which is T over S, and we look at it in the cosmic sector, then that would be their velocity. T over S would be their velocity, and energy would be written as S over T. Of course, they would change the labels just like we do, so one would look like the other, but you get the idea. There are 2 sectors of the universe. One is the reciprocal of the other. So we've written here our number line as it would normally be, and then we've written here their number line. I say there as if there are other living beings that are made of these particles. And their particles are our antiparticles, and our particles are their antiparticles. So now this is an amazing thing. Einstein, when he discovered what he discovered, he didn't write the dimensions of mass as S over T over S cubed times S over T squared. He didn't think in those terms. That wasn't until Xavier Borg came and showed how that we can write all the SI, the International Standard of Units, can be written in terms or reduced to terms of space and time. And before people knew that, then it was not written in that way. It was written as E equals MC squared, and nobody thought of it in terms of space and time. But if we look at what Einstein accomplished, we can see that there's some confusion here that needs to be straightened out. The space-time dimensions of E equals mc squared are TS. Let's see, and I think I must have a chart on this, but I must have skipped it. Is it that one? I guess that's the only one I have. I thought I made another one, but evidently not. Anyway, we can see that they could just be multiplication factors. We showed that. Let me go back to that one. At least got something right there. So, but does that mean that the energy E is just the inverse of the speed of light, C? That's really a strange concept, if so, because then it must be a coincidence that the dimensions of mass, T cubed over S cubed, are the dimensions of 3D energy, or a volume of time over a volume of space, which is even stranger. See, in the legacy system of physics, you can't think of time that way. Time is strictly a scalar. Well, it's not necessarily all that strange. Einstein, you see, if you understand what he did, he deduced that famous relationship between mass and energy based on the fact that the energy of light carries away kinetic energy. It turns out that his kinetic energy calculations between moving bodies had to include a difference between the time that was progressing for the emitting object and the time progressing for the observer, which was different. And finding a difference implied that this time difference then would affect the frequency. And if it affected the frequency because of the equation of energy and the role that frequency plays in that, frequency times the Planck's constant, then the energy being carried away by that radiation would be different. But since that difference in energy loss is due to the relative motion between the emitting object and the observer, which can occur either before the relative motion is introduced between them or afterwards, the sum of the kinetic energy in both cases is different depending upon when that motion occurs. So this seems like nonsense. How can it make a difference of when the motion occurs? But turns out that since the velocity in both instances is the same, and the kinetic energy formula only contains those two terms, the velocity and mass, he had to conclude that it was the mass that had to change. And this conclusion then led to the famous equation and its later verification by experiment. But the experiments placed a limit, or seemed to place a limit, on the relative speed of matter. And the conclusion from that is that no aggregate of matter may exceed the speed of light. But see, that doesn't necessarily mean that there are not aggregates of matter on the other side of the speed of light, like in our teeter-totter example. And so this really leads to some results that are truly amazing in terms of what we can find in the universe. That probably doesn't make any sense to you, Roy. I'm sorry. I even gobbled it up so much that it probably doesn't make sense to anybody. But did you get anything out of it at all? Well, he may not be by the microphone. But my point here in all of this, and of course I can't take credit for understanding this, it's just what I have studied and gained from Dewey Larson's ideas. But it's amazing. Hey, did you hear any of that?
Yeah, I heard a little bit of it. I cut my finger removing trim around the room, and I had to go bandage it. I was bleeding.
Oh,
pretty good.
Well, I'm sorry. I have a little
Above my head.
A little video I want to play because what I was explaining, I was trying to explain how, from Einstein's point of view, see, he didn't get this from understanding that mass times the square of the speed is equal to energy in terms of dimensions, space-time dimensions. He got it from a wholly different approach, And then that's what it turned out to be. And now that we know that the dimensions of space and time can be, or are the real dimensions of the universe, that we can take kilograms and meters and seconds and all of that and reduce them to meters and seconds in every case, it changes everything, because now we can go back and look at Einstein's equation and see how different we can get a different view of what's happening there. So we'll make that more clear as these what do you call them? Lectures. Yeah, these lectures go on. But it turns out then that the bottom line is we have these different number systems, but we also have these 2 points of view of the number systems. We just took one of the 3 number systems as an example, but because we know that the natural progression is measured as space over time, then it's identical to a measure as time over space at the unit progression. There, it doesn't matter, right? I mean, 1 over 1 is equal to 1 over 1, even if you turn them upside down. It doesn't matter. If space, 1 unit of space for 1 unit of time gives you the speed of light, then if you turn it around and you get 1 over 1, as far as the numbers are concerned, 1 unit of time for 1 unit of space isn't any different. They come together at that point, right? It's only when you start deviating from unity that it turns out that you've got a mirror image. You got 2 possibilities. One is the mirror image of the other. We call it the reciprocal. So if we call one the space over time and the other time over space, then when we look at these at the different numbers that come out by combining these progressions that we talk about, we call them LCs, then we can see that there's really a whole new world opening up. And none of it is being surmised. We're not guessing. We're not proposing. This comes out of the mathematics. It's I can't think of the word that I wanted to use, but it's very rigid. You know, there's no room for different to go about it a different way. It comes out and very rigidly, and that's the only way that you can come out that way. So these relationships are strictly mathematical, and they're a consequence of the first fundamental postulate of the RST, which assumes that space is the reciprocal of time, or vice versa, and what the properties of one are the properties of the other. But Einstein says, well, there can't be any speeds of matter aggregate, because the mass, it can't be over this unity because the mass goes to infinity. Well, that's really not the reason. And so over unity may be an impossible speed for matter aggregates that are formed on the SOT sector of the universe, as we've seen them emerge in our standard model of the LST community's particle physics. But obviously the mirror image of matter aggregates could emerge on that other side, on the time over space sector of the universe as well. And by the same logical deductions, we can develop either one of them. It depends on our point of view, though. See, we can take either point of view, but one is the reciprocal point of view of the other. I hope that makes sense. And it's consistent on either side, but you have to be able to deal in the terms that are consistent on that side. So as a result, then, the TOS matter aggregates would be subject to the same speed limit as SOT matter aggregates, but in the opposite direction. So the faster they go, as they approach the speed of light, they cross over that and they become slower. From their point of view, it's faster than the speed of light, but from the point of view of on the other side, it's actually slower, and it slows down to actually to zero. So that's amazing. But with this much understood, we can see then that matter aggregates that are entering from for whatever means, it might be violent explosions or whatever, but they're entering from one sector, from, let's say, the time over space sector, the TOS sector, they would have to exceed unit speed, and then they would slow down on this side, while matter aggregates on our side entering the TOS, the time over space sector, would have to exceed unity from our point of view and then slow down on the other side from their point of view. So Einstein's findings place a unit limit on the speeds of all space over time matter, which is well understood in the theory of special relativity. And it's been proven over and over that it works. But we can also see that under unity speeds must exist in the time over space sector too. See, here's the bottom line, Roy. If we say that matter can't go faster than faster than the speed of light from our point of view, then we would be saying that they can't have matter aggregates of speeds less than the speed of light on their side. So if we eliminate it on one side, it eliminates it on the other side, which does violence to the mathematics, see? So now Dewey Larson named the space over time sector of the natural progression the material sector, and I showed that in that one slide. And then the time over space sector he called the cosmic sector of the universe. So what we have to understand, though, is that vector motion, that is motion of objects in the material sector, is motion in space, while the motion of objects in the cosmic sector is motion in time. See, this is perfect reciprocity between the two, like a mirror image. The consequences of this theoretical development are just enormous. And the new multidimensional scalar number system that we can now see in the same terms has to inevitably play a big role as we explore them. It enabled Larson to explain the origin of cosmic rays and to predict what came to be known as quasars a year or so after he predicted their existence when they were discovered. But he predicted them before they were discovered, and based on this whole idea of faster than light speeds. And of course, it promises to yet unravel many mysteries of our physical universe. So I wanted to play, though, so we can see, I wanted to play this video it's called The Mystery of Cosmic Rays. So you have to read it and have to kind of follow along with it, but I think you'll find it very informative because they can't understand how these cosmic rays, which really started the whole field of particle physics, studying them, they cannot understand where they're coming from. But we know where they're coming from. Now, with the reciprocal system, they're coming across this speed limit. But anyway, let's watch this. Oh boy. The system doesn't always work the way it's supposed to. Okay, here is the bottom line of the whole thing. You have all these this energy coming in the form of light. They're calling them rays. You got gamma rays, X-rays, ultraviolet rays, visible light, infrared, and radio waves in the whole spectrum. But these things that are very, very high, highly energetic up in the gamma ray area, and it's coming to the Earth from outer space, as if it's coming like there was a big invisible shield around the Earth, and out of that shield, like we're on the inside of it, and out of that is coming these cosmic rays that are coming at us from every direction. He sees it's not coming from the sun. But it's coming from outer space, everywhere in outer space. That's the amazing thing. We call them cosmic rays. Now, see, the amazing thing is that they're composed of subatomic particles that penetrate to the Earth's atmosphere from space continuously and reach to the Earth. Most of them reach clear to the Earth. So we're being showered by these particles that are coming from everywhere. It's not known exactly how he's got a few typos in this, but how these rays are formed in space. Well, I'll say it's not known exactly. It's not known at all. It's a complete mystery. But from the reciprocal system, we see that this is actually matter that has been accelerated beyond the speed of light, but in the reciprocal cosmic sector, if you will, of the universe. And the same thing when we get these huge explosions in our sector, it accelerates matter beyond the speed of light, and they become the cosmic rays of the reciprocal sector, the cosmic sector. So it all makes a lot of sense. 40 million times the energy level that is in CERN, the LHC, they call it, Large Hadron Collider, that they built to collide protons together. And it's the highest energy we've been able ever to reach on Earth. And yet these cosmic rays, these particles coming in from an unseen sector, are 40 million times higher than the highest energy of the CERN. So, of the LHC in CERN. So you can see, and now that we have the mathematics to calculate this, we ought to be able to show eventually that those when they're in that speed, the speed of light, but now it's time over space, and their motion is actually in time and it comes into space as it's converted, then hopefully we can find those relationships and define them mathematically. Well, I don't know who made this, but it's interesting. Even though he might be a foreigner whose command of the language is not complete, but at any rate, there you have it. This idea of cosmic rays, and all of a sudden it comes out of the reciprocal system. Of course, there are many more details that would need to be understood, but I encourage you to take a look at the system. Hopefully we've piqued some interest here, although I probably have to apologize for the way I present these slides. I still don't have a satisfactory way of doing it where I can see everything I need to see when I need to see it. So anyway, Roy, do you have any questions? Did you know about cosmic rays before? Well, you may be tending to his cut finger right now. But anyway, so that's it. I hope it makes sense to somebody. If you have any questions, we could take them on Skype. Never really tried that. I was going to have my brother try Skyping me now to see how that worked, but it turns out that we'll have to do that another time. So, seeing there are no more questions from our vast audience, we'll leave it there for now, and till next week, we bid you adieu.